Friends, we pick up with one more question. The crystal system of a compound with the unit cell dimensions, make a note, A equal to 0.39, B equal to 0.39, C equal to 0.65, given in nanometers, and the angles alpha, beta and gamma equal to 90 degree is. So first of all, what is meant by A, what is meant by B, and what is meant by C. About the unit cells, the dimensions for the unit cell, we can see here, it carries the length, it carries the breadth, it carries the height. Length is given with A, breadth is given with B, and height is given with C. And the angles, we call them as edge angles, alpha, beta and gamma. Alpha is the angle which is seen between the breadth and height, and beta is the angle which is seen between height and length, and gamma is the angle which is seen between length and breadth. With the help of these edges and the edge angle, those 7 basic unit cells are developed, like the monoclinic, triclinic, tetragonal, hexagonal, orthorhombic, rhombohedral and cubic, like that. So here we elucidate the unit cell and its the crystal system this way. If the A equal to B, length and breadth are equal, but the height is unequal. A is equal to B and not equal to C, while all the angles are equal and equal to 90 degree. And this is nothing but the tetragonal system. So tetragonal system is something which can be visualized with the unit cell of this type. It carries the length and breadth in equal dimensions, but the height is unequal, that is the value of the C. Angles are equal and equal to 90 degree, and therefore our option goes with tetragonal unit cell and tetragonal crystal system. And here one more information that I would like to pass on to you is about the cubic. Some are very simple to remember and carry on with further informations. Cubic is the one where we say all edges are equal and all angles are equal and equal to 90 degree. All edges, length, breadth, height equal. All angles equal to 90 degree. While the last, that is the triclinic, here we have the total opposite characters. All edges are unequal, all angles are unequal, and they are not equal to 90 degree. One, the most symmetrical cubic, and another, the most unsymmetrical triclinic. Coming to this orthorhombic, here we have length, breadth and height, the edges. Edges are unequal, but the angles, alpha, beta and gamma, they are equal to 90 degree. Can you recall such a type of the geometry in some of the day-to-day used materials, like it is the matchbox. In the matchbox we see length, breadth and height are unequal, but the angles, they are equal. So that is how the 7 unit cells are individually distinguished with the help of the length, breadth, height, and the angles present in between these dimensions. Then we come to next question. Sodium and magnesium crystallize in BCC and FCC type crystals. So what is the BCC and what is the FCC? BCC is the short form for body-centered cubic lattice, and FCC is the short form for face-centered cubic lattice. And these lattices have their own unit cells, which we popularly call them as BCC unit cell and FCC unit cell. And the unit cells of these two metals here, the BCC and FCC type crystals, the number of atoms of the sodium and magnesium in these unit cells. So how these number of atoms or number of particles can be calculated in the unit cell? Now look, calculation becomes very, very simple. For that, we have to remember these four types of the lattice points which hold the particles in the unit cells. Number one, it is the corner lattice point. Number two, it is the body-centered lattice point. And number three, face-centered lattice point. And number four, edge-centered lattice point. Contribution-wise, we say corner particle makes a contribution of 1/8 towards that unit cell, because that corner is going to be shared with the other adjacent unit cells. One corner, one unit cell, 1/8 contribution. While the face-centered lattice point, it contributes 1/2 of the particle to that unit cell, because a face is being common to two unit cells. Therefore, per face, per unit cell, contribution will be 1/2. And the edge-centered particle, it is making the contribution of 1/4 towards the unit cell, because the edge is common to 4 unit cells. It has to be shared among the 4 unit cells. Per unit cell, the contribution works out to be 1/4 particle, while the body-centered lattice point, it makes the contribution of only one particle, entire particle to that unit cell, because that particle is not going to be shared among other unit cells. This way, BCC unit cell, if observed in sodium crystal, and what that BCC unit cell is, see here. This is the BCC unit cell having the corner particles as well as the body-centered particle. This is the body-centered particle. Now the calculations are very, very simple. From 8 corners of the unit cell, the number of particles will be 1, because it is 1/8 from one corner, and into 8 from 8 corners, the particle is 1. Body-centered particle, it is a particle of that unit cell. Therefore, in case of the sodium, the number of particles is 2. While in the magnesium, which comes in FCC type unit cell, face-centered cubic unit cell, that unit cell is shown with the 6 faces carrying the additional particles at their centers, and of course the corner lattice points are common and they are a must. So here, from 8 corners, the number of particles will be 1, as in the previous case. This is the contribution from 8 corners. And from the face, each face contributes 1 by 2 particle. 6 faces will be giving a total of 3. So the number of particles in the FCC unit cell is 4. Thereby, Na carries 2 particles and Mg carries 4 particles in its unit cell, and there we can easily go for the option 2 and 4, that is the D. This way the particles can be worked out.